Thanks very much, Bert. So, excuse me. So Bert asked me to speak about matters that I found interesting within the program, and a little bit like Janusz, I interpreted that as thinking that I'll talk about some things which maybe weren't covered so much in the program, and that are important, and we might possibly have thought about them a bit more. So, why am I interested in? Why am I talking about statistical modelling for planning and policy applications? Well, one point is that it matters quite a lot. Three examples of this are thinking about variability and uncertainty of renewable resource. So this is a matter of inferring information from data. We have uncertainty in planning background, which we need to manage somehow if we're looking to use modelling for decision support on planning and policy timescales. And we also have the minor business of linking modelling studies to the real world. So important to note, I'm not a statistician. So my first degree is in maths. I have a PhD in physics, master's in operational research, and I'm a chartered engineer, so that's the British equivalent to professional engineer, member of the OR Society, IEEE. So I'm not a statistician, but where I came to thinking about these things, it to some extent originates in how people think about modelling in the area of theoretical physics I was in. So one of the first things you learn is that if you have a model with a large number of parameters, no one will believe anything you say. And a large number of parameters in that context would be, say, 3. And so there was one thing that Amy Wilson and Michael Goldstein and I dealt with, where the input space was 10 squared Excel spreadsheets. And so we're in a slightly different world there. These matters of statistical modelling associated with planning and policy timescales haven't been covered so much on the Newton Institute programme, and as far as we can see, there isn't a lot of involvement of professional statistical modelling in this anywhere. We certainly found it difficult to identify people for the second workshop on planning and policy. So statistical work, I mean, we have had quite a lot of good statistical work during the programme. It's mostly been associated with short-term forecasting. Where you have work on capital planning optimisation, this often concentrates on how you do the optimisation side, doesn't look so much at how you actually come up with the uncertainty specification or generate your scenario tree. And this is, so I was very pleased that Laura, the previous speaker, did discuss these matters of elicitation to some extent. This is something which matters. It's not something we've looked at so much, but currently are in the Centre for Energy Systems Integration. Another thing is that working out what models are telling us about the real world, or as opposed to about the model world, is not particularly fashionable in energy systems. I mean, one other way of illustrating this is that I'll talk a bit about resource adequacy risk assessments, and I just listed here the people who I'm aware of who have applied some sort of professional statistical thinking to this. The question mark ones are people who might not be called statisticians by origin. These are all the people I'm aware of who have ever worked on this, who in some sense are applying professional statistical thinking. And given that this is largely an applied statistical question, there aren't that many of them. So there's a lot of open space here and something that really matters. What I'm going to talk about, resource adequacy risk assessment, which is a matter of inference from data. We'll talk about some of the specific issues in capital planning when we're dealing with large-scale computer models that have very complex backgrounds. going to talk about, and I'll also talk about some scoping projects that I've been involved in. Okay, so when we refer to resource adequacy, we're talking about the absolute risks of supply capacity, and this is something where occasionally energy systems analysis tends to hit the popular media. So this is an example from Texas. I can say exactly, I think the most famous example is the California blackouts in 2000-2001. So this wasn't strictly a straight engineering issue of lack of capacity. There were market issues mixed in here as well. But it does illustrate why political level cares so much about this. So this is the former, well, at the time of this article, he was Gray Davis, governor of California. He was partly as part of the sort of general malaise that led to his the recall election, where he was ceased to be governor, was arose from the California power crisis, and of course he was replaced in about 2003 by this gentleman. And then, just to illustrate how this hits the media in Britain, so I can say exactly where I was at 6 p.m. on the 5th of October 2012. So I got back home at 6 o'clock, at the time when I still did occasionally get back home in time to put the 6 o'clock news on, and found that this project I'd been involved in with National Grid and Ofgem was the lead headline. So I started thinking, this isn't the usual business of academic research anymore. And then we can go a little bit further, because there is actually one person there is actually one person who's spoken on this programme who's had a big photo of him in the Sun newspaper, which is Britain's biggest selling newspaper. So there was this was the year after. What we typically found is that when this study came up with some kind of pessimistic results, then it would make big newspaper headlines, and then if it said things were looking okay, then no one would care. But Andrew Wright, who spoke in the second workshop here, it was actually a very fair report in the Sun newspaper of what he'd said about the latest study in 2013. So what we're interested in here is basically the bookkeeping of available supply versus demand. Adequacy is a notoriously intractable thing to define verbally, so I tend to take as the quick way to say these are the kind of mathematical models that we refer to as adequacy models, and then think, what real-world situations are these actually relevant to, rather than trying to define in a quick way the other way round. So we're interested in the bookkeeping of available different resources above demand. Ahead of time, these are of course all random variables. Might include interconnections to other systems or storage in there. Might have, and then risk indices we typically define. Well, the classic risk indices which are used are the expected duration of shortfall in a future season conditional on some state of knowledge. You might look at energy-based indices, and you could go a bit further and look at go into more detail, and sometimes look at the probability distribution of duration of shortfall or energy not supplied, or you might try to make some kind of monetary quantification. Well, one thing here is this is, as I say, this is basically, a lot of these questions are basically applied statistical questions, and there hasn't been very much professional statistical thinking applied. So there's a lot of open space for research here, because we do get some quite subtle modelling issues. So the first point I'll mention is where one might, if you think you've got 10 years of data, you have a lot of numbers, but how much information do you actually have? So, and this just illustrates from work by Amy Wilson, Zachary, that you have this grey splodge, which is this huge list of numbers that you have, but these contours in the bottom right are illustrating the extent to which, depending on how high demand is or how low your available wind is in Britain, these data points contribute to the risk calculation results. So essentially, you can have, particularly at very high scenarios with very high wind penetrations, you can have results being driven by a part of the space where you have very, very little data. And just to illustrate this again, this is a similar scatter plot, just looking at times of the wind resource at times of daily peak. The black line is simply basically a moving average. So it seems that at times of very high demand, the mean is maybe going down a little bit, but you have very little. But what really matters is the points in the red circle, where you have very little data to turn in this either way. So this data set includes 7 years of data, but it includes the most recent cluster of extreme winters. So if you might look at different ways of estimating distribution of demand net of wind, and probably the most common approach is to so-called hindcast, where it's predicted distribution. You just use empirical historical distribution of net demand. You could instead of bring more data in by assuming general independence, or you might assume independence between distribution of available wind and how high demand is on a particular day. It's probably an assumption too far, because everything is driven by the weather. Or you would want some particular evidence for this. You might bring in longer meteorological time series to help bring in more data, but certainly isn't yet any settled approach in the literature. I think that we might have some hope that when we publish current work on this, that might. It would be nice for us anyway if that did become some kind of settled approach, but we'll see. You also have an issue. You typically have limited numbers of relevant years. So this is a plot that was produced by National Grid in one of their reports a few years ago, and there's as well as any sort of headline risk index, there's interest in how high risk level is conditional on severity of winter. And this. When National Grid produced this plot, it was quite striking to people. So they produced this plot basically. Suppose you used each of these different historic years as an example of what might happen. This is how high the risk level might be, and the response came back from some people in the industry or policy world. What do you mean that if you have a colder winter with higher demand, then the risk level is higher? Yes. But there certainly is interest from high-level decision makers and analysts in this kind of variability. But the fact that you have a relatively limited number of historic years is very chancy business, trying to sort of jigsaw together synthetic winters by putting together bits from different real winters. But you, in a sense, you can only really think of yourself as picking up one data point per year for this purpose. And then and particularly given that extreme winters tend to cluster, so you tend to get. We had a cluster. You can see here we had a cluster of extreme harsh ones in 2008 to 11. Another in 2012-13. Then coming up with some sort of unconditional headline value of risk index is problematic. and I mean, what you certainly have is a list of examples of historic years, and you have limited ability to turn that with a great deal of confidence into a distribution, a possible profile of future years. And then you also get into some interesting questions here of relevance and the frequentist interpretation of probability, when you only get one shot at a particular winter. And you certainly don't have the ability to run repeated trials. They're also, again, another kind of underlying thing is one of these kind of bits of important enabling things that often gets a bit forgotten about because it's a bit bread and butter and not particularly glamorous. Is simply how you map historic years' demands onto some sort of common future scenario of underlying demand level, because you have all kinds of issues of underlying demand growth, the profile of different components of demand changing. This really matters when you're doing these kinds of calculations. There's very little there's very little careful work on how you should go about that. Are we calculating the right thing? So I've already hinted that expected value indices are used in most industrial and government studies here. The exception to this, is there anyone from Belgium here? Yeah, yes, except Belgium. So the Belgian, you're not supposed to be able to read this URL. I just put it there for if people download slides. The National Grid discovered that Belgium is the country, and does seem to be the country in the world which looks at a probability distribution of potential outcomes conditional on scenario. Because these expected value indices are not everything. The question that the decision maker might ask is, how bad can things credibly get? And of course, expected value indices by definition contain no information on variability about the mean, and more generally, expected money does not represent the way that real decision makers think on planning and policy things. It might be analytically tractable, it might be computationally tractable, but it's not how people tend to think. And one point in is that there is almost, you need time series modelling if you're going to calculate a wider range of indices. But there seems to be almost no work in the literature on time series, serious time series, joint time series modelling of Wynn and demand, or modelling of net demand for this purpose. And we have one paper in preparation, but we're really not aware of anything else. An example of why one might wish to do this. This is a paper from the Probabilistic Methods Applied to Power Systems conference a few years ago. It was a kind of simple numerical experiment where we sort of fixed the headline expected value index, have different Great Britain scenarios which have the same headline risk index, but different amounts of wind generation connected, and we basically look at the probability distribution of energy unserved. And we found that for the same headline risk index, if you have if you go from having 0 wind installed to 30 gigawatts installed, then the probability of something really bad happening in the model might vary by an order of magnitude. And it's kind of you expect it to be obvious intuitively that if you have greater variability of supply, you'll have greater variability of outcome. But this does illustrate how potentially, if you stick to the classic indices, you could think you're maintaining similar risk level, but actually you're quite radically changing the risk profile of the system. Again, in order to be able to do this, there's much more statistical work that's required. Okay, validation of models is also a good idea. So I won't go into too much detail about what we have here. This is a nice piece of work by Kevin Cardin and colleagues at Strape in Atlanta. And they were comparing two different ways of generating from the same data a distribution of available conventional generating capacity. So the blue series is what you get if you apply the standard modelling approach for constructing a distribution where you assume independence between units and convolute distributions for each unit together. The purple line is the empirical historical distribution. If the assumptions underlying the standard modelling approach were in any way relevant to the world in this particular system, these would look quite similar, and they kind of don't. But it does suggest that some of the assumptions about independence between units and so on that absolutely everyone makes everywhere may be a little bit heroic. And if there's not so much thinking about this in the context of statistical modelling floating around in the context of wind and demand, there really isn't very much in when it comes to conventional generation. Conventional generation in many systems is, of course, what we're really relying on. So the real thing is that the real concern is that you see much fatter tail of the empirical distribution, that the events that will get us into that would actually really get a system into trouble are precisely ones which have been excluded implicitly from the model by the assumptions made. Of course, the third thing is that extremes matter, because I mean, in almost all risk calculations. Well, if your events which if your events which are really in scope for risk calculations aren't in the tail of a distribution, you probably don't have a very viable system. So I'll just give a brief summary of what we've what's mainly what Amy and Stan with me as a little bit of an occasional hanger-on have done in applications of extreme value theory in this context. So a few years ago now, Amy and Stan did some work with National Grid, looking at the one area problem where we're basically looking at modelling a univariate probability distribution of net demand, and this is a relatively straightforward thing to do in terms of mechanics of doing it in using extreme value statistical methods. I mean, there's still some very careful statistical thinking required, but it's thought that there's something reasonably definitive there as an approach that can be applied. We also had a project looking at equivalent time series modelling, and I think it's there are people that are better placed to comment. Yeah.
What is the model? Because like I see your points out front of it.
Oh yeah. This was just this was just simply fitting a generalised Pareto distribution to the tail of distribution of net demand to provide some smoothing. There are people, well, for instance, Bert, who are better qualified than Bert and Stan and Amy, who are better qualified than me to comment on all detail of this. But once you get beyond one dimension and independent data points, then you're pretty rapidly in extreme value statistics find yourself heading towards the frontiers of what methodology exists if you have a particular practical application. But we also had a project looking at time series equivalents, where hopefully we'll have a paper coming out fairly soon. But don't ask me for the detail of this one, ask Stan and Amy.
Chris, just while you're here,
yeah.
it might be nice if Amy or Stan, I don't know if this is for now or later, would comment on, when you're in the tail, you've got so little data has been pointed out. I don't know if those pictures it looks like I'm seeing data points with a line going through them, but
Yeah.
the ones I'm familiar with are data points that stop and the line keeps going.
This is I think this is kind of in the tail because it's above 45 gigawatts. So there is some data in the tail. So I think the actual smoothing kicks in about probably at 50 gigawatts.
I guess what I'm asking is if you're worried about the system falling over, you're worried about events you haven't seen in the last 7 years or whatever. And so presumably that's why you're doing these calculations, but I'm not seeing any gaps. Aren't you doing sort of extrapolation because you're obliged to? That's really what I'm asking, and I'm not a statistician.
I don't think we've kind of completely cracked the idea of the very rare events with this. It's more just the sort of rare events in the sort of data that we have.
I see.
So
but when you advise policymakers, are you kind of hinting that there could be worse? It's just even more rare, or?
Well, we try to do this for each year in our data set, and there's only 10 or something, and show how it varies quite a lot between the years, and that gives you some idea about how you can have these rare events like in 2010, and it causes things to be very different all of a sudden.
But something rare over 100-10-year period may be quite difficult to predict.
Yeah, and that's something that we're interested in, but we haven't.
Oh, I mean, it's
that's a constant conundrum with
Yeah.
public policy in particular. There are these sort of ultra rare events you really would like to worry about, but they become increasingly difficult to attach probabilities to. You just have got to realise at some stage that the possibility is there, and understand what you will do.
All right, thank you.
It has to be realistic.
Just a comment on this. Do you have a consensus on how you want to quantify a rare event? Is it an exponentially rare or?
Well, shall I try this one and see if Stan or Amy would remotely agree with what I say? There are theoretical grounding behind the idea of using a generalised Pareto distribution to fit the tail, and these plots basically illustrate that generalised Pareto was a very good fit. I mean, what we found is go on, Stan. You were grimacing.
So I just think I think that what is going on, everybody who works with extreme value theory knows this, what is going on in the tail is obviously extremely dodgy and for obvious reasons.
Yeah.
And generalized Pareto is generally a satisfactory first approximation in a sense, in real world applications. I don't think that's dodgy, really. I mean, not particularly dodgy compared to the typical extreme value theory situation.
Yeah,
quite used to that.
Yeah, but the key, I guess I mean, just going back to Danny's question, the key thing is which part of this range is dominating risk calculation results. I mean, here we have what the fact we got lots of data there is illustrating that the data look like generalized Pareto, not just in what you would think of as the extreme tail. But the key question is, in a given application, is it only this bit of the range which is really contributing? In which case you do have fewer data points. One thing is unless you've done something like this, then you're flying a bit blind.
Well, even if you have done it.
But of course
you will never be able to see.
Yeah, but of course you've still got the possibility of some horrendous thing that is completely outside your historic data that might come in. So, for instance, if you've been doing a study in the US before polar vortex conditions happened a couple of times, or in Britain, what if we had a repeat of winters like like the one in the late 40s or 62, 63, you maybe don't have an ability to extrapolate onto those by looking at historic data. But you've got two things. Number one, what does the data you have from, if you like, a given year tell you about years like that? But then you maybe got the second question of what years could turn out like, and you kind of get completely different natures of years that you just haven't experienced. Anyway, the other thing we have a student who's just started now looking at this two-area systems. So we're starting off looking at joint modelling of Great Britain and Ireland, and again, this is something where there's the sort of, if you like, barrier that just the level of subtlety increases very greatly, going from looking at Great Britain in isolation as a single zone to looking at the two zones together. Okay, so I'll talk a little bit of the second thing I'd like to talk about in terms of specific technical issues is looking at large, what happens when looking at capital planning decision support and large computer models. So in terms of, we had a little bit of mention in the previous talk about some of the range of uncertainties that we might wish to consider, but there's a useful taxonomy of different sources of modelling uncertainty, which Amy's and my collaborator Michael Goldstein often uses. So, and I kind of this apart from the animations, this slide is taken almost directly from one that Michael uses. These are sources of uncertainty which people typically have in their mind, even if they don't really do much about managing the consequence uncertainty. Ones in bold are ones which are again maybe a bit less in people's minds, or certainly are very, very rarely treated head on. And then the key methodology point which Michael works on is what he refers to as functional uncertainty. So that, which is basically is that you have a finite number of evaluations of your model, often a small number of evaluations, and the places where you haven't evaluated the model matter just as much as the ones where you have. And then it's actually in this room last year, Michael also mentioned that an important thing is uncertainty about what people mean when they say uncertainty. So very, or probability. So very often people might make statements of uncertainty conditional on certain assumptions, and one great problem in communicating outside the world of modelers is these conditional statements of uncertainty end up being interpreted as unconditional statements. Again, when you have statements about probability, what state of knowledge is this conditional on? What is actually meant by it? A good example of that is the weather forecast I was looking at this week to see if we could have a drink outside last night, and it gives a certain percentage for rain on the BBC website, and their assessment is probability of 50% that it will rain at some point in the hour, or at any point in time probability of 50%, and expect it. Are they saying that they anticipate rain for half of the hour? These are common things in when you get these in quite serious policy reports. And the sort of the resolution which is used by people like Michael and Amy and I've been involved in is the idea of the statistical emulator, which essentially encodes your state of knowledge of your the value of the output of your computer model at the places where you haven't run it. Because as long as you can make some sort of assumptions of smoothness, if you have something that's bouncing around all over the place, you've got no chance. But if you can make some sort of assumptions of smoothness, you can build a statistical model of the behaviour of the computer model. A simple example of this, of what you would do with this, is suppose you have some probability distribution representing uncertainty in the value of the inputs, and you want to propagate this through to uncertainty in the value of outputs, then because the emulator, this sort of surrogate model, is quick to evaluate, you can use this to propagate the uncertainty. But also, if you've only been able to do a small number of runs, you can use this in a natural way to combine the uncertainty in inputs with the uncertainty arising from the consequences of a number of small runs. So you get so in that sense you're able to get away from the dependence on the choice of evaluations, or at least work out the consequences of the fact that you've only done a small number of evaluations. I mean, another benefit of this is that it gives you a framework in which you can consider a full range of modelling uncertainties. And we've had in looking at optimisation modelling, we've had some discussion during the programme of how there are, in that sense, in terms of the ability to bring in a full treatment of uncertainty, there are in principle great benefits to this, but the difficulty is that relatively little is known about how to do the optimisation computation that would be required. So we could, a couple of examples of this. One is looking at contribution of interconnection to other systems to security of supply. There's a lot of interest in this in Great Britain, and other systems will have similar issues, but I mean, it's a little bit different if you're on continental Europe because we're in Ireland and France isn't. You have two linked issues. One is that given that we currently have about 3 gigawatts of connections to the continent, which is going up a bit, but not that much, there's absolutely no way that you'll be able to improve your state of knowledge of what Europe looks like to the extent that you can, that simply uncertainty arising from the fact you don't know what Europe looks like is smaller than your interconnector capacity. And the other thing is that any credible model of the European system will be very complex, high-dimensional, slow to run. And so if you actually want to learn things about the world as opposed to about particular point estimates of parameters that you've made, then I think how you go about doing this is an open question. Of course, you may get mixed up in all kinds of nice questions and multivariate, very high-dimensional multivariate time series with focus on extremes. Another example, which is this one is actually taken particularly from energy, but it's the same issue. So this actually came from the preparations for the evidence-based decision-making for UK Landscapes programme in July. This was this is an organogram of basically an organogram of the countryside, which was produced for the Department of the Environment, Fisheries and Rural Affairs a few years ago. And the fact that you can't read any of this is basically the point. That this kind of high-level organogram is horrendously complicated. So the organogram has become known as the horrendogram, suppose you were to build some sort of model at this level of detail, it still would be getting absolutely nowhere towards the complexity of the real situation. And when people are looking at these the decision support models for planning and policy things, the Markal, for instance, was name checked in the last talk. But it's very difficult to make arguments linking to the real world through bottom-up system modelling, because the real world is just so much more complex, and you have such almost unlimited uncertainty looking out decades as to what the background will be. And this is confronting this issue head on, and thinking how do we construct logical arguments to help take good decisions for the real world, as opposed to optimal decisions for some sort of model world is it's something that, I'd say, is rarely confronted head on. I'll just briefly mention capital planning optimization. This is the point. The only thing I'll really say here is that it is the computational point that we currently don't know about how to use this emulator framework in a Bayesian decision environment. But essentially, what you end up with is we have a I'm actually quite surprised. I think I've ended up being the first. I'm certainly the first person I've seen use the blackboard in this talk. Someone was expressing great pride in the new blackboards. What you'd have in a traditional optimization problem is something like that, where you have a nice crisp objective function with a well-defined optimum. If you're considering full range of uncertainties in modelling, then what you would end up with is something like that, where you're not quite sure, because of all these uncertainties, you have some sort of confidence bound on the objective function. So what you actually get into at any point is working out which points can credibly be ruled out, which points can't credibly be good ones, and that space search for ruling out points seems to be something where there's relatively little is known, and it's probably quite a hard problem. I'll just also mention one final technical thing of the question of right for the right reason. And one thing we have had quite a bit of talk about is cascade events and blackouts. The key point there is that you're dealing with very, very complex situations. It's typically in blackouts the case that some kind of very fine detail, some sort of weird event, like a hidden failure, is implicated. And it's a great challenge knowing that if you have a model that reproduces some aspect of the statistics of real world data, whether it really is the modelling whether it really is the modelling, the assumptions in the model which are the explanation in the real world, or whether in some sense you kind of got lucky. And it's very good we have people like Bert and Adam who are working on this, who very properly understand these issues. Just coming to the conclusion of some of the scoping work that we've done, I remember once coming to the I was in discussion with a prominent energy systems modeler from the mainstream community, and I was trying to get away from talking about any specific methodologies for uncertainty quantification, or in other words, trying to say something that wasn't too direct a paraphrase of the solution is for people to give Amy and Michael and me more research funding. But I came with the idea that the sort of minimal requirement for an applied modelling study being that there should be a clear statement of what the study is claiming to say about the real world, along with a logical argument to back this up. And when you look over a lot of published studies that have become very prominent, then many fall over on the first point, never mind actually having a logical argument. So it's worth it. So I'll just finish by summarising a couple of scoping activities that I've been involved in. So I think it's about 2 or 3 years ago now. We ran hosted by the regulator Ofgem. It was actually hosted by Andrew Wright. We hosted a scoping workshop on needs for R&D in modelling to support energy policy, or some very snappy title like that. We had quite a wide range of attendees, a lot of interest. We were a little concerned that we'd get from this a sort of shopping list of specific pieces of technical work, and this was kind of precisely what we didn't get. There was a great deal of, and I mean, the sort of headline areas that came back were there was a lot of interest in management of uncertainty in energy systems modelling, and I think particularly how this can be done in practice in the field, because it's one thing having methods in principle that can be used by mathematical sciences academia. It's another thing entirely having methods which can be used very broadly in government or industry analysis. Communication modelling results beyond the technical modelling community was regarded as important, but and that one is really very much to be expected. And the third one, there was a lot of importance placed on not just thinking of technical modelling in isolation, but thinking of of how modelling sits within overall decision processes, and the sort of human and institutional side of how all of this works. One document which might be interesting is the government aquabook. You can find this just by googling Treasury aquabook, which is the nearest thing there is to an official manual of what constitutes quality analysis in UK government. It's an extremely high quality document within its scope. So what it does is say what people should be aiming for. It actually makes what in any kind of applied community are really radical statements about what is required. But out of scope for this is how you actually go about doing it. I think there's quite a bit of concern at the moment that there's this manual which people might be held to, which in principle requires some quite radical things, but they're not sure how you actually go about doing this. A more in-depth process was a research scoping network which I led for the Centre for Digital Bill Britain on methodologies for planning complex infrastructure under uncertainty. They're actually based about 10 minutes walk away at the West Cambridge site in Cambridge. We had. I won't go through the sort of, obviously with something like that, much of what comes out of it is things you already anticipate. Of course, again, these things do matter, so matters like managing uncertainty, communicating results, how things fit within an organisation. I mean, more intriguing matters or less obvious things that came out. It was felt there was a lot of need for enabling work on the current state of knowledge and practice in industry before certain types of research projects could get going. There was a desire for a more nuanced understanding of failure and success of projects. Often in the media or politics, this is regarded as a kind of binary thing. And does your new railway come in on time, on budget? Because all these things are a kind of spectrum of possible costs or times for a large project. And in some cases, an overrun might not really be anyone's fault. For instance, civil engineers would probably put this a little bit more intelligently, but you might come across a type of rock that you weren't really expecting or something, and this is part of how it goes. But you could have a much more realistic debate if there was some way of communicating this reality to the public debate. Communication is a two-way process. Often communication is thought as being something that modelling community does towards decision makers, but it was also felt to be very important that the analysts have a proper appreciation of the interests of the decision makers. So basically, they're actually doing relevant analysis. Felt that often the resource allocated to analysis for strategic planning. So this will be the early questions of what do we build, how big, is often not commensurate with the potential capital budget of a project. Because when you're dealing with a £10 billion project, you you don't want to be counting the pennies too much on deciding whether to do it, because there's clearly potentially very large benefits from better analysis. Various points about use of scenarios in decision making, which is a whole topic of its own. Using modelling to help de-risk contracts, how you do offline analysis to support development of engineering standards, which can be applied rapidly in the field. Interest in enabling activity on data availability. We heard a bit about that on Wednesday from National Grid and Co. in the Open Business event. Also, it's important to design any funding calls to enable interdisciplinarity. So because it's often the case that funding calls somehow end up being designed so that people who already have lots of funding in the particular application area get more, and sometimes the way funding calls are designed can create barriers to important methodology disciplines coming in. There are some of these issues might well be addressed in the evidence-based decisions program at the Newton Institute in July. I've already mentioned that that there are similar issues around, say, very complex backgrounds to policy decisions. And one feature of that program is that it's part of a major research council funding and research agenda in that area. So that is an example of where mathematical science as a linked into the mainstream of the research council and government in a particular application area, which I think is very positive. Finally, I'll just finish with some references. One thing I would flag is, unfortunately, I only found out about this research group in Cambridge, I think last week or the week before. We were struggling to find statisticians at to speak at the second workshop, and if I'd known about this at the end of last year, we certainly would have invited, I think, Rishi Chowdhury to speak. And she's been doing some very good work on this in uncertainty quantification and energy modelling, expanding out from building modelling into wider system modelling. So I think it's worth just name checking her as someone significantly involved. And the rest of this is references associated with what I've already spoken about. Thank you very much.
Some further questions?
So today, supply adequacy is based on meeting peak demand with dispatchable generation. I wonder how long that's going to be sufficient. So at what stage do, for example, very low net demand, where the majority of demand is being met by uncontrollable generation, and actually operability becomes the factor?
Yeah, there's a one point. One kind of general point on that is there's a sense in which, unless you get to really having very little dispatchable generation on the system on a operating time scale, that's more of a sort of economic question than an outright engineering reliability one, because in system operation decision making there are things you can do about this, like just turn off all the wind generation in principle. It might cost you a lot, but you can do it, whereas if you just simply don't have enough capacity, then you're stuck. But yeah, once you get, but I mean, in terms of how you have an economically designed low carbon system, that is a very big issue, and I mean, I think where we are coming to some issues in Britain is having which are genuine engineering issues, is that it's possible that in 10 years' time there will be no large conventional generation in Scotland. So we'll have major engineering issues in supporting voltage. The other point where this obviously issues are different where you have a very large storage capacity, but the other point where which really would change this is if we had a great deal of demand response. Because a lot of the reason why we have capacity markets is associated with the fact that, say, on an operating timescale, you get to the point where demand is just fixed. Whatever the price does, demand has no way of responding. So you have to do involuntary disconnection. But if you did have much greater demand response, then that's one circumstance under which, and if the price went very high, then a lot more would come forward on short time scale. That's one circumstance under which you maybe would have more of a conventional market.
Maria, last quick question and a quick answer.
Sorry, just related to this question. So I think these questions really raise the issue about who does what statistical modeling, right? Like if you have forward markets and binding commitments, then there is much more certainty provided for the future by the distributed resources, and then there is probably a little bit of minimal coordination for predicting what happens on the interconnected system. Right now, the US is struggling with that for the case of Puerto Rico, because it's a very interesting case, because there is going to be maybe 60% on the distribution side, distributed resources, and the question is who is projecting uncertainties, right? So I guess at the end of the day, the question is, do we need to rethink our statistical modeling into more of a distributed, interactive statistical modeling? I haven't seen any of that.
This is one point. This is related to a challenge that National Grid posed earlier in the programme about would their system operation costs be reduced if they had better information on what's in distribution networks. Currently, I think by nameplate, National Grid have basically no visibility of about a third of generation. That's rapidly heading to a half.
So other methods to be developed on the.
I think one question there is, there's a sort of institutional point of do we kind of leave the situation as it currently is, and we basically try and come up with clever ways of operating the transmission network, and when eventually we might get to a stage where National Grid hardly has visibility of anything, or do we put a different institutional framework in place where National Grid have much greater visibility, and so with some of these things, they could be solved by kind of clever things that we do, or they could be solved by redesigning the rules on who has what information.
But actually, to beat it to that, they're all going to create risks themselves over different time horizons. So, who is going to pay for different type of risks? Markets worry a great deal about that, but I think there is you don't have statistical tools to propose some framework where you would actually push that, because I don't see top down, even the talk before that, you can never predict, right? Uncertainty. Sort of non-granular uncertainty is just going to kill us.
Yeah, and I think with a lot of these issues associated with institutional framework for distributed generation, we've already got a lot of it, and we don't really have a workable overall framework. We're going to have a horrendous quantity of legacy arrangements, which somehow we might have to unravel, or people will say, well, no, we signed this contract, we did it under these rules. And so when you get half of your nameplate capacity there, then trying to unravel current arrangements for half of the generation is going to be not nice.
MIT is proposing now for Puerto Rico these, not me, broader themes. They are proposing this interactive approach to planning in Puerto Rico, because there are so many private, public entities that want to do something and just cannot be related at all to projection of demand, where demand could change this way. So it's an interesting experiment, I think.
We have a break now. Thanks again, Chris.